Hi, everyone. My name is Dorsa Sadigh. I am an assistant professor in the computer science and electrical engineering departments at Stanford. I'm also part of the AI Safety Center here. And my research is about robotics and robots interacting with people. And today I would like to talk a little bit about safety in robotics in the context of interacting with people in, let's say, near accident scenarios or near the end of the risk spectrum. Let's talk about this in the context of driving. So imagine an autonomous car driving down the road. And if you think about autonomous driving in the past decade has made a lot of advances. We've seen these vehicles driving now on the road as opposed to driving down the highways. And then lots of interesting behaviors interacting these vehicles interacting with human-driven cars and other drivers on the road. But one of the big challenges that these vehicles have is basically trying to balance between safety, efficiency, comfort, and then these different objectives that different drivers might have. So let me make this a little bit more concrete with this plastic bag problem that I've been discussing with people. So imagine that there's a plastic bag on a road, and the question is, how should the autonomous car treat this plastic bag? When it sees the plastic bag, should it slow down or should it continue going? So what it can do is, one option is it sees the plastic bag and it looks like an obstacle, and it could be a person like holding that plastic bag, and it might decide to just slow down every single time it sees a plastic bag on a road. And that's not going to be so great, because that would result in the person or passenger inside the car feeling really nauseous, this vehicle keeping like braking and being very uncomfortable, going against the comfort or efficiency of the vehicle. On the other hand, the car might decide that, well, this was just a plastic bag. I shouldn't be that worried that there is this plastic bag on the road. I'll detect it as something that I shouldn't worry as much, and maybe I can just continue moving on and go forward. And once in a while, like, you actually make a mistake and your sensors fail, or you don't realize that it's actually like an obstacle, a real obstacle. And because of that, you end up in crashes that are kind of unexpected and not so great. And we have seen some of them already. So this is a very difficult problem. In general, autonomous vehicles, they need to balance between this trade-off between safety and efficiency. And I'm kind of like putting all these different objectives under these two big categories of, should I be safe and should I be worried, or should I be efficient and comfortable for the human inside of the vehicle? And this balance particularly becomes important when we are in near accident scenarios. In general, this balance is important, but when you think about near accident scenarios, this balance becomes much more critical, because we are in this safety critical situation. So what I'd like to do today is I'd like to focus on these near accident scenarios, characteristics of these near accident scenarios, and I would like to talk about two main topics. First off, taking a very data-driven approach and trying to go and learn a policy for these autonomous vehicles when we are in near accident scenarios. So what we propose is using ideas from imitation learning and reinforcement learning in order to have a vehicle that can drive in these near accident scenarios based on data collected in these settings. And in the second part of the talk, what I'd like to do is I'd like to look at it from a different perspective and try to predict how humans drive, how human-driven cars around me drive when we are in near accident scenarios. And for the second work, I'll take more of a model-based approach, trying to understand how we can use ideas from behavioral economics or prospect theory to come up with better models of how vehicles around us drive and how they treat risk when we have humans in the loop in these settings. Okay, so that's my plan for today. All right, so let's just jump into it. So what is it that makes near accident scenarios special? So one interesting characteristic of near accident scenarios is this idea of phase transitions. So you might have a vehicle, an ego vehicle, this red car down here, and it's driving down an intersection, which there's an occlusion, so it doesn't necessarily see the intersection very well. And it's just driving down the road, and the environment is really changing very smoothly in the views of this autonomous vehicle, this red car here. And as it goes down the road, there might be this blue car that's coming down, and the blue car might keep going, and because of that, the autonomous, in this case, the red car, the ego car, needs to slow down to avoid accidents. But what is really happening is that there are these smooth changes to the environment. Like when you observe this blue car and the environment in general, it smoothly changes from the viewpoint of the ego vehicle. But if you think about the actions of the ego vehicle, what the ego vehicle actually needs to do, it ends up slowing down very abruptly. And we see this change of mode like immediately coming out here. Like you were driving down the road and at some point you have to press the brake and you see a very big shift in the acceleration of the ego car. And then we're calling this phase transitions more generally. And these phase transitions, they kind of create a set of modes in driving. They create a set of natural modes in driving. For example, we might have aggressive driving where this vehicle keeps going forward, the red car keeps going forward, or we might have timid mode where the vehicle actually slows down. This corresponds to directly slowing down. Or we might have other types of behaviors like swerving. So the interesting thing here is that a lot of near accident scenarios are actually defined by this idea of having phase transitions, big jumps in the actions of the autonomous car. And I'd like to emphasize that these phase transitions naturally create a set of discrete modes that we need to deal with. As much as I hate discretizing the world, I do think discretization here, like between these modes, actually makes sense when it comes to thinking about how we transition and how we drive in near accident scenarios. So I think then the interesting question here is if I'm planning on driving, if I'm planning on coming up with a policy for the autonomous car here, that question boils down to this question of how do I switch between these different modes of driving? What would be the optimal switching between these different modes of driving? So what we propose is in order to come up with a policy for the autonomous car, we can treat that problem as an imitation learning problem at the lower level, where for each one of these modes of driving, one can try to collect data. Here we're collecting images of a car driving in a carless simulator, but one can collect a bunch of data of how cars drive in each one of these modes, and then train a neural network where this neural network will come up with a policy for each one of these low-level modes. So we have this conditional imitation learning algorithm for each one of these modes of driving and a policy for each one of them. And then finally, at the top level, this vehicle needs to basically decide what mode it is picking, and that ends up being a reinforcement learning problem at the higher level, deciding between what mode you should be in. And this approach of having a high-level reinforcement learning and low-level imitation learning is actually very scalable, because if I were to apply reinforcement learning to a driving problem, it would blow up really quickly, the state space will explode. And at the same time, imitation learning here is much easier because we are looking at specific modes and specific driving behavior. And even with limited data, we are able to run imitation learning at the lower level. So the algorithm we are proposing here is what we're calling it H-Trail. It's a hierarchical reinforcement learning and imitation learning algorithm, which basically has this high-level planner that runs a reinforcement learning agent, switching between these low-level policies that are learned through imitation learning. So we have actually evaluated this on a variety of near-accident driving scenarios. We have scenarios like the cross-traffic example that we saw, or like if a vehicle is coming down in a wrong direction or making an unprotected left turn, or what if like a car slows down right in front of you and stops, how would that affect your behavior? And we've also looked at this merge behavior. I'm only going to show one of these examples, but this is a work that we have published at RSS this year. So if you're interested in any of these other ones, we have videos of these results of these different interactions. All right, so let's look at the merge scenario. So the merge scenario is a scenario where we have an autonomous car. That's the red vehicle. And the red vehicle wants to change lanes and it wants to go to the right lane. And it wants to do that fairly soon because there's an exit that's coming up. And the idea is if it should go ahead of the blue car or if it should wait for the blue car to pass and merge behind him. So those are kind of the options that it needs to decide on to be safe, at the same time to be efficient, to try to exit relatively soon. So here what we are comparing is on the left, we are comparing an imitation learning algorithm only trained on timid data compared to an imitation learning algorithm only trained on the aggressive data. So when the imitation learning is trained only on timid data, the vehicle ends up just merging behind the blue car all the time. If it is only trained on the aggressive data, it always goes ahead and it kind of gets close to the intersection, which can be dangerous. If it is trained on all of our data, we end up getting weird compounding errors, so the vehicle goes a little bit offside. And then using our algorithm, depending on the scenario, this is only one run of it, depending on the scenario, it decides to balance between safety and efficiency. So looking at the results of this, if I compare collision rates, which is safety, and completion time, which is a proxy for efficiency here, we see that our algorithm, HRail, which is shown in orange, is going to be relatively safe. Of course, it's not going to be as safe as the timid imitation learning algorithm, but it is very safe. And then at the same time, it's very efficient. Again, of course, it's not going to be as efficient as the aggressive imitation learning algorithm, but it acts very reasonably, and it figures out how to balance between safety and efficiency in this particular environment. In addition, we did a user study where we basically asked to rate these different driving behaviors on a 7-point Likert scale. And our users significantly preferred the policy that was generated by the HRail policy as opposed to some of these other methods and baselines. So the key idea here that I've been trying to discuss is the fact that we are integrating reinforcement learning and imitation learning in order to drive in near accident scenarios. And we're proposing a method here that figures out how to balance between safety and efficiency when it comes to near accident driving scenarios, trying to drive a vehicle in these more challenging settings. And this was work that was presented at RSS this year. Zhang Jie and Erdem were and Woody were the main authors of the work. All right, so now we have talked about learning policies for autonomous cars in near accident scenarios. Now what I'd like to do is I'd like to switch gears a little bit and think about how other cars around us drive in near accident scenarios and how we should respond based on that. All right, so I think we all agree if we have a robot or if we have an autonomous car that's acting in the world, these vehicles or the robots need to be able to predict how the humans around them or how the human users or operators, in this case, are going to act and react to the human. I don't think that's a new idea. In general, we should be able to model humans around us. But the question is, if we go to slightly different scenarios, more safety critical scenarios, for example, a human on a factory floor, or a person, a pedestrian in a near accident driving scenario, the question is, do these models that we are making of humans, do they still hold true, or are they going to change? And if they are going to change, how are they going to change? So let me motivate this a little bit with an example. So imagine we have, again, a driving scenario. Again, the red car is the ego car. And what the ego car wants to do is it wants to make an unprotected left turn. So our red car is our autonomous car. It wants to make an unprotected left turn. Okay? And there's this blue car coming down the road, and at some point, the light is going to turn yellow. So when the light turns yellow, the red vehicle should try to predict if the blue car is going to pass the light or if it is going to stop. And if the blue car assumes that this vehicle is going to be a rational agent and an optimal decision maker here, based on that, it would decide that, well, the blue car, based on its reward function, it should be stopping soon because the light is going to turn red. And if it is stopping, the best action for itself is to make the unprotected left turn because the light is going to turn red. But the thing is, I think we all have seen cars passing yellow lights or red lights. And in general, if you're making robots or autonomous cars that are interacting with humans in these settings, these autonomous cars or robots need to be able to predict and recognize that humans can act suboptimally in risky scenarios. And that's exactly what we would like to be able to model. And so far, most of our models of how humans act around us, like building behavioral models in driving or in robotics, it's all about basically modeling the human as an agent who is approximately or fully optimizing a reward function, RH here, and basically saying, well, the policy of that human agent is going to be an optimizer of that reward function. So this is the simplest form of a human model where we assume that there exists an optimal action and the human is going to be rational and take that optimal action. More recently, in recent years, people have been realizing that humans are not deterministic and they're not deterministically going to take the rational optimal action. And a more recent method is modeling humans as agents who are noisily rational. Basically saying, well, humans are going to be probabilistic, so their actions are going to be probabilistic, and probability of actions of humans is proportional to exponential of some theta parameter, theta here, times the reward function. And this theta parameter is kind of like a temperature parameter, and it's commonly referred to as a rationality coefficient. If you set that equal to infinity, then you're going to get your optimal action. And then if you set that equal to 0, you're going to get random actions. And basically, you can tweak that theta to get any curve that looks like one of these gray curves here. But the problem with the noisily rational model here is that it still assumes that humans are most likely to take the optimal action. And these models are not able to capture the fact that, hey, like humans are actually sometimes very likely to take something that is suboptimal. So for example, the most likely action of the human could be passing a red light. And if that is the most likely action of the human, then we should be able to capture that. And the way we try to do that is by capturing that by model that kind of like looks like the orange line here. So the question is, how can we build a model that looks like the orange line here and is able to capture that? So the idea that we use here is we don't change our model much. Like we don't want to come up with a whole new formal set. And what we would like to do is we would like to say probability of actions of humans is still proportional to exponential of some theta times some reward function. But this reward function should be able to capture the fact that humans tend to be risk-averse. And then this reward function, the way we are modeling that is by using ideas from cumulative prospect theory. So what we do is we make a set of nonlinear transformations on the original reward in order to capture a curve that looks like the orange curve here. And these nonlinear transformations are nonlinear transformations on the probabilities and on the reward values that's able to capture the fact that humans act differently when it comes to near the end of the risk spectrum. So more specifically, imagine the reward is a sum of product of probabilities times rewards of events, like passing a red light or not passing a red light. And then we look at probabilities and rewards and we make nonlinear transformations on top of them. So imagine the true reward being the dotted line. And then the risk-aware reward will be a nonlinear transformation that's shown in orange here. And that is parameterized by a set of hyperparameters. And this is able to capture the fact that, well, humans are having a hard time differentiating differentiating between high reward values compared to low reward values. Like this is the same phenomena when it comes to thinking about value of 10K. That value of $10K is going to be a lot more if you're comparing it with $1, but 10K doesn't have that much value, like if you're thinking about $1 million or $1 million and 10K. So that is going to be captured using these nonlinearities here, as you see in this plot. Similarly, we can think about probabilities, and then same notion, probabilities are going to also have a set of nonlinear transformations on top of them when you're thinking about risky scenarios. So specifically, this is the same phenomena that we see when we look at buying lottery tickets or buying insurance, right? People tend to overweigh low probability events and underweigh high probability events. And we should be able to capture that in our human models when it comes to these risky scenarios. All right, so just to summarize, so what I've been doing is I've been taking the reward function, the usual reward function that one can use to model how humans act around us, and I've been suggesting making these nonlinear transformations on that reward function in order to be able to capture the fact that humans are going to act differently in risky scenarios. So we've been trying this out actually in a driving scenario to basically see if our model is able to predict how humans drive in near accident scenarios. And it turns out that we ran a study, and it turns out that in our study, low risk scenarios tend to be scenarios where humans are acting suboptimally. That's when the majority of people tend to act suboptimally. And if you think about this scenario, this is the result of the study, how humans actually act in this setting. If you take this data and use the noisily rational model of the human versus our model of the human, the risk-aware model, it turns out that both of them are perfectly fine at predicting high risk, how humans behave in high risk scenarios. But when it comes to low risk scenarios, which is, remember, when the human was acting suboptimally, when it comes to low risk scenarios, our risk-aware model is actually much better at predicting how humans are going to act in these settings. Similarly, these ideas go beyond driving. We actually wanted to run an experiment where we have a robot planning based on these models. So we created an experiment where we have a human and robot together trying to build a tower, putting cups on top of each other and build a tower. And in this case, the human and robot together have two options. They can either build an efficient tower, but unstable tower, kind of like the Tower of Pisa. And if they build that tower, they get a lot of points. They get 105 points, but the tower only stays upright like 20% of the time. On the other hand, they have this option of building an efficient tower, but stable tower. And that tower never falls, but they only get 20 points when they build that tower. And the question is, which one should they build together? And if you think about the optimal thing to do, the optimal thing to do is to take risks, to go and build this unstable tower. That would be the thing that gives the higher reward. And a robot that tries to work with a human, a robot that would assume the human is going to be noisily rational, it would assume that the human is going to be most likely to take risks. And because of that, it decides to go for the orange cup. But it turns out that in this scenario, the human is going to act suboptimally and being kind of like overly concerned about the tower falling and also going for the orange cup. So because of that, the robot needs to replan and go and pick up something else and work with it. You see this in action. So here the user goes for the orange cup. The robot also goes for the orange cup because it doesn't realize that the human is going for the orange cup. And because of that, it needs to replan and go and pick up something else. Similarly, if you think about the risk-aware model, our robot in this case is going to be able to predict that the human is going to be overly concerned. And because of that, it just goes and picks up something else. You see that in action. Robot just directly goes for picking up something else because it knows the human is going to be not taking risks and be suboptimal. So just to summarize, the key idea here is that we need to capture the suboptimal human behaviors. And the way we do that is by using ideas from cumulative prospect theory in order to predict how humans act in near accident driving scenarios or in general in the near the end of the risk spectrum scenarios. And this was work that we presented at HRI this year. And just to summarize, I really think when it comes to near accident scenarios, we should be a lot more careful about how we are planning for our autonomous systems, how we are planning for our autonomous cars. And we need to be much more careful when it comes to predicting how humans act and coordinating and collaborating with humans. So with that, I'm looking forward to seeing you at the panel, and I can take any questions there. Thank you.